I'd like to tell you a little bit about CASTEP. First of all, to tell you a little bit about what it does. The aim is to predict materials behavior from first principles. What that means is not having to know what it does beforehand. So not having to know whether your material is a metal or an insulator or whether it's chemically reactive or not. The idea is that we can essentially just put the fundamental physics into the simulation and all the properties of the material will emerge. So that's the idea, and we do that by solving our quantum mechanical problem using density functional theory, which has already been name-checked several times, at least 2 talks. So I won't go any further into that, but of course you're welcome to ask me about that later if you like. From a computational perspective, CASTEP was created in the late 80s, but I and 5 others rewrote it at the end of the last century, with these principles in mind: to be portable, efficient, parallel, and user-friendly. Fortran 2003 was the language, well, not in 1999. Fortran 95 was the language, but we've since updated to Fortran in 2003, and we make heavy use of maths and FFT libraries. And for parallelism, it was originally written just with MPI, but has been extended to have OpenMP threading as well. It's available freely worldwide for academic use, and it's sold commercially to industry by OVIA. And the core development is done in the UK at the Universities of York, where I am, Royal Holloway, Oxford, Durham, and Cambridge. And Cambridge is where the other half of the GPU team is based. So what does CASTEP do? It solves the density functional theory equations iteratively, and it does it in a basis which is a Fourier basis. So we use the fact that materials are periodic, and we can use that 3D periodicity as our basis. We diagonalize a large matrix, the Hamiltonian matrix, and we diagonalize it iteratively, and that requires applying this Hamiltonian matrix many, many times. So I've split the Hamiltonian matrix H into 4 parts, and the first one, T, is the kinetic energy, and that's diagonal in Fourier space, so it's trivial to apply that, so I'm actually not going to talk about that. The next bit is called the local potential term. You don't really need to know what that is, but that's diagonal in the direct space. We then have what's called the non-local potential, which is essentially a low-rank matrix update. And finally, for some classes of calculation, Hartree-Fock and hybrid calculations, we have this term called the non-local exchange correlation term. And that's going to be an aspect of our work, as we'll see in a few moments. But to start with, I'll start at the beginning of our story of the GPU port. So for the GPU porting project, we focused on applying that Hamiltonian matrix, and we decided on OpenACC, following our original principles of portability and easy development. We use OpenACC to generate kernels and manage data transfers, but the idea was to drop in QBLAS and QFFT, where we currently use the BLAS and the FFT libraries on the CPU, and of course QSolver or perhaps Magma as the LAPACK equivalent. The CPU still handles the communication. So the first thing we did is, of these 4 terms, we took the non-local potential application. This is the low-rank matrix update, so it's essentially, it looks like a matrix-matrix multiplication. The CPU time is spent entirely in BLAS, so we use OpenACC to transfer the data to the device, and we use QBLAS for the operation. This was done by research software people in Cambridge, the CST3. And the initial performance was encouraging. So we ran one of the benchmarks. It happens to be solid benzene. That's not particularly relevant. This is on the previous GPU machine in Cambridge. So you can see that it's Ivy Bridge and K20, so not particularly up to date. But the important thing to notice is that we got speed-ups almost straight away. So all we did was offload this one part of the application, and we were getting speed-ups of 1.4 to 1.7 immediately. Now, this is partly because it is quite an accurate calculation where the non-local potential takes a slightly larger proportion of the calculation as normal. But we were very encouraged by this because it was relatively straightforward to do. And we're already seeing speedups. And this is not one core on the CPU. This is using the 4 or 12, or as you can see, 24 cores compared to the two K20s on each of the nodes. So this is a sort of a whole system comparison. So emboldened by that, we looked at two other performance intensive parts. So that's the local potential and, where appropriate, this non-local exchange correlation. The thing that these both share is they both make heavy use of fast Fourier transforms. And anyone who's done a fast Fourier transform in high-performance computing will know that the word fast is rather subjective. And in fact, they're often bottlenecks in parallel performance. In particular, NLXC is almost entirely fast Fourier transform bound. And here we have a distinction between the different parallel modes that you can run CASTEP in. So if your Fourier components of your solution are not distributed, you can do a 3D Fourier transform. But if you've distributed those over a set of nodes, then what we do is some 1D Fourier transforms, and then we use MPI to do a all-to-all, which is essentially a transposition. So we do the 1D FFTs along one direction, let's say Y, then we do a transposition, and then we do the 1D FFTs along X, and then a transposition, and then along Z. Again, OpenACC manages all of the data transfer for us, and now we're using QFFT for the operation. So I'll show you, as time is short, I'll just show the NLXC results for this. So for one of our particular benchmarks, this happens to be a Heusler compound, iron vanadium aluminide, which is an interesting thermoelectric, but we didn't choose that particularly to showcase the GPU. That was just one we were interested in scientifically. And you can see that our initial GPU port is getting a 6-fold improvement over the CPUs. This was fantastic and rather blew away our previous non-local potential offloading. If we look at that a little bit closer, although it is a 6-time speed up, if we work out the FFT should be memory bandwidth dominated, that's what we expect on a CPU, we're getting less than half of the memory bandwidth speed here. So we might expect to not get 100%, but why is it less than half? So we profiled this, and what we see is that the time is spent an awful lot in launching kernels and synchronizing. So this is a story you've seen before, that we've got a lot of short kernels being launched. About 60% of the time is spent launching the kernel, and 30% of the time is spent synchronizing. So there's an awful lot of waiting involved here. The actual compute is going very nicely. If we look at that visually, here is our timeline analysis. So I don't know whether that's big enough for you to see, but the important thing really is that we've highlighted a couple of operations here, the sort of turquoisey and the blue, and then there is an awful lot of just blank space where nothing much is happening. And that is obviously incredibly bad for performance. We're launching lots and lots and lots of these kernels, but we're spending an awful lot of time just hanging around waiting. So what we did next, and when I say we, I mostly mean my PhD student, Matt Smith, who's done the lion's share of this as part of his PhD. He refactored a lot of the FFT kernels that we use and fused the OpenACC kernels, and he also reworked some of our loops to batch up the FFT. So Martin referred to some similar work in VASP to this, and I just want to illustrate really the tremendous performance advantages, because if we do nothing but that, and now do a timeline analysis, this is what we see. So now you can see that instead of all of these areas of white space, we're essentially seeing continuous occupation of the GPU amongst the different kernels. The white areas are, they're actually 2 pixels wide on this plot if you zoom in enough. And we get substantially improved memory bandwidth. So we've gone from less than half to between about 92 and about 96%, I think it is, of the memory bandwidth here. This was done, I think this particular timeline analysis was done at the hackathon at Oak Ridge last year, so this was on Ascent. And if we compare what the refactored GPU performance is, we've gained more than a factor of 2 over the initial GPU. In other words, we're between 14 and 15 times faster on the GPU compared to the CPU. And this is the CPU using, this is one MPI process per GPU. The GPU was a V100 here, and using OpenMP threads to occupy the rest of the node. From memory, I think there are 42 cores per node. So this work has been done not by me primarily. It's been done in collaboration between researchers at York and researchers at Cambridge. Particularly, I'd like to call out Matt Smith, my PhD student, who's really done the lion's share of all this. We've had a lot of support from NVIDIA as well, particularly Levi Barnes helped us in the early days, Alan Gray at the hackathon last year, Alexei Romanenko at the most recent Sheffield hackathon, Kaveh Mood at Jülich, and Ada Sidova at Oak Ridge as well have been very, very helpful. And I should thank EPSRC, who funded my fellowship, my research software engineering fellowship, which has funded my time on this. But what I'd really like to focus the last minutes on is what we found with regard to the technical aspects here. So the initial port, OpenACC, was a very low barrier route. We already had OpenMP, and OpenACC syntactically is very similar. It was very easy to write OpenACC directives throughout the 500,000 lines of code to get some GPU offload and even in many cases some acceleration. However, producing something that's close to the peak performance of these GPUs has been considerably more work. So even back to the early days, actually profiling and having a look at the timeline analysis has been crucial. Now, of course, that's important even on the CPU, but it really has highlighted the importance with the GPU. Debugging on the GPU has also been a problem. In particular, if things don't work, it can be much harder to work out why they're not working. So is the data on the GPU synchronized with the CPU or not? Well, the GPU doesn't generally have an easy way of outputting what's on the GPU, so it means dragging data back from the GPU to look at it. And of course, that raises the possibility that you write bugs in your code to do that. So there are many challenges. The data transfer is our main challenge at the moment. And again, Martin touched on some of these issues. This is really how do we best overlap the launch of the kernels, the data transfer, and the actual work on the GPU. And one particular thing that we would benefit from when we're using multiple MPI ranks to share a GPU, which is sometimes necessary in order to make full utilization of the GPUs, to saturate the GPUs, sometimes each MPI rank is multiplying, say, some matrices together. One of the matrices might actually be identical for each MPI rank. At the moment, every MPI rank is copying that matrix over to the GPU, even though other ranks may have done the same thing. And it would be extremely useful for us if we had access to, for example, CUDA shared memory. One rank could transfer that, and we could then use that copy of the matrix on all the data that all the ranks are sending. So, for example, if C is A times B, A might be replicated on all the MPI ranks, and you could only have a single copy on the GPU. And then B would be different for each of the ranks. That would save us some time in the data transfer. It would also keep the memory usage on the GPU down, which is a limiting factor for us as well. 16 or 32 gigs is not a huge amount of data, particularly if you only have 1 or 2 cards per node. A second issue, we've worked very hard to use modern software engineering practices in CASTEP, and that means encapsulating data and code. But that's made it rather hard to optimize the data movement. In OpenACC, it can be very difficult then to understand. You want to go into the low-level matrix multiplication routines and offload those, but the data that they're acting on is declared several source code levels up in not just a parent or a grandparent, but a great-grandparent routine, and that can be really difficult. And without adding a lot of metadata everywhere, it can be quite hard to track where was this array allocated, How are we passing it down? How do we know whether it's properly synchronized or not? So that's a challenge for us. But I think more widely, it's a challenge for us as a community to think, how do we maintain good software standards and the efficient use of OpenACC? The next challenge I put here, I've already touched on really. When we're running an MPI parallel with multiple cores on the CPU, but possibly multiple GPUs, what is the best mode of operation? Do we do, as we did on the Ascent data I showed, pin one MPI rank per GPU and use OpenMP to sort of occupy the other CPU cores? And if we do, then how do we get OpenMP for the CPU to play nicely with OpenACC? And this, again, I saw as a theme on the Q&A earlier. Or do we do many MPI processes which share the GPUs, perhaps using something like the multiprocess server, at which point we have this problem where we need to be able to access the GPU shared memory to cut down on our data transfer. So again, which is the best model here, or is a hybrid model the best? From our point of view, the jury's still out, and we would welcome experience from OpenACC experts, but also other application developers. For us, I think the next step is to look at distributing the FFTs without involving the CPU for communications. And that's where the CUDA-aware MPI comes in. And that's our work, the work in Cambridge at the moment, to implement that. And at that stage, we'll be able to look a little bit more widely at non-blocking collectives and maybe nickel and other things. But for now, I think that's me, and I hope we should have plenty of time for questions. So thank you very much.